Okay, let's talk about the magnetic quantum number. All right, so we talked about the principal quantum number n, which can start at values of 1 and go up in integral numbers, so from 1 to 2 to 3 to 4. We talked about the angular quantum number L, which can start at 0 and go up in integral numbers from 0 to 1 to 2 to 3 up until n minus 1, which means that there's a restriction on the angular quantum number based on the value of the principal quantum number. All right, now the thing is this. When you look at the angular quantum number, we already stated that a value of L equals 0 is associated with an s orbital. A value of L equals 1 is associated with a p orbital, but the idea is that you actually have 2L plus 1 possibilities for the orbitals. And in the case of L equals 0, that means that you only have one possibility. There's only one s orbital for any given energy level that you may be looking at. But for the p orbitals, in which L equals 1, if L equals 1, 2L plus 1 will give you 3 possibilities. And what that means is that you actually have 3 different kinds of p orbitals present in any one energy level. And specifically, what you can see is that you have the same type of shape for the p orbital. The only difference is that one of them is pointing up and down, another one is pointing left and right, and the third one is pointing in and out. Now, if we continue in the series, L equals 2 implies that we're going to have a total of 5 d orbitals present. And the d orbitals roughly kind of follow the same idea as the p orbital, meaning that you take your butterfly shape and you basically kind of move it about in space. On one instance, you could have it on the plane of the board, or you could have it going in and out, but also left and right. You could have it going up and down and going in and out, or you could have it going in and out and left and right. But in addition to that, you may have noticed that there's this funky orbital that kind of looks very different from the rest. This is also a d orbital, and it also does have 2 nodes present in it. We have a node present over here between the unshaded lobe and the middle donut, which is shaded, and then we have another node between the donut and the lower node itself, the lobe itself of the orbital. Now for the values of L equals 3, which correspond to f orbitals, we now have 7 possibilities. And there are 7 f orbitals that actually do exist and play a role in the chemistry of certain elements. Now, I personally don't want you memorizing how to draw the f orbitals. I'm keeping them here, for good measure. They're kind of interesting to look at. But the ones that are the most important for you to know are the s and p's. The D's, I'm gonna maybe discuss them in some degree. I'll probably, have you remember 1 or 2 out of them, but it is important that you kind of take a look at the overall look of the orbital. And notice that all of these guys right here have 2 angular nodes present in them, whereas the p orbitals only have 1 angular node. The s orbital has no angular node, hence the fact that it is completely spherical in shape. All right, now this kind of brings us to the m-sub-L value, the magnetic quantum number. The m-sub-L value is actually a representation of how many types of orbitals we can have present for any one type of orbital that we're dealing with. And technically speaking, it's literally given by the total probability number that we see here in this column, 1, 3, 5, or 7 different orbitals. But more specifically, the m-sub-L value assigns a number to each one of the possibilities for the given orbital. So notice that for the s orbital, m-sub-L is just 0 because you only have one orbital. So you basically go with the same number as L. But in the case where you're now looking at the p orbitals and there's 3 possibilities, each one of these orbitals has a unique m-sub-L value associated for it. We start at -1 and we go up to +1. And in a similar fashion, if you look at the d orbitals, we also have a unique number of m-sub-L associated with each individual orbital, each individual d orbital. And we start from -2 and go up to +2. Notice that all the values are integral values, whole numbers. We don't deal with any decimal numbers dealing in regards to the quantum numbers themselves. Finally, for the L equals 3, notice that we start at -3 and we go up to +3. And that's actually kind of like the main premise right here. If you take the value of L, start from negative L and go all the way up to plus L, that will give you all of the values associated with the M sub L number. And specifically, that is the one restriction of the magnetic quantum number that you need to know. So right now we're looking at two restrictions altogether. Whatever the value of N is, restricts the maximum value of L. L can go up to N minus 1. And for whatever value of L we have, the values of M sub L will be restricted from minus L up to plus L. And you will always go in whole number integral values from whatever negative L is up to whatever positive L ends up being. But I also want you to notice that there's only one s orbital per energy level. There's 3 p orbitals per energy level. There can be 5 d orbitals for energy levels. And there can be a total of 7 f orbitals for any energy level in which they may be present. So each one of these things if you look at them, they have some trajectories, some directions associated with them. So not only can you describe the orbitals based on their M sub L numbers, but you could also give them names based on where they're pointing in the direction. If you look at this Cartesian coordinate with the z-axis points up and down, the x-axis points left and right, and the y goes in and out, then you can say that the p orbital shown here that's going left and right, well, that coincides with the x-axis, so this will be known as the px orbital. And the one that's going in and out, well, that coincides with the y-axis, so that's known as the py orbital. And then, of course, the one going up and down is the pz orbital, basically telling you which direction you have the orbital located in. These kind of have a similar idea, but they're a little bit more complicated because you're dealing with two dimensions now in terms of the directions. For instance, the first orbital here, notice that it's going left and right, which coincides with the x-axis, but it's also going in and out, which coincides with the y. So this one is called the Dxy orbital. The one over here is going up and down and left and right, so that coincides with the x-axis and the z-axis, so it's known as the Dxy. The orbital right here that goes in and out and up and down coincides with z and y, so it's known as the Dyc. And the one that goes left and right and in and out, you might want to say, oh, well, that matches up with x and y, but we already have a value associated with one of the orbitals with that name. So this is actually known as the x squared minus y squared orbital. And the last one, the one that's unique in shape, is known as the Dc squared orbital. These particular orbitals are going to be very important in terms of remembering how they look and what they are when it comes down to Chem 12 and we start talking about transition element chemistry. For now, I'm kind of going to have you to remember, the shape of the butterfly shape and the shape of the funky Dc square orbital. Those will be the ones I kind of want you to keep an eye out for. The f orbitals, I'm not going to bother you with the names because they're just complicated. The most important part though is associating the magnetic quantum numbers with the given orbital sets that you're dealing with. Okay, so with that in mind, I'm going to stop the video at this point.